What's up my friends, welcome back! So, I'm working on a lot of projects, and a lot of them require a design PCB. I've already designed a few professional PCBs and I'm very proud of the results. So I thought it would be great to make a small example tutorial and show you how to edit your PCB in order to CNC mill them and obtain great results. You can use any program that you have, they should be almost the same and the design rules are always the same too. I've learned how to use and only use since then a program called Design Spark that you can download from a link that you will find in the description of this video. It's not the best, but does his job. I've designed a small PCB of a mini drone right here in Design Spark and turned out pretty well. I've CNC milled it and soldered all the components. It works perfect. So let's get with the tutorial. As always in a project you should first have an idea. After that is the simulation. Once you simulate your circuit in a SPICE program, you should make some breadboard tests. When the tests are done, you have to make the schematic of the circuit, and using the schematic you will finally make the PCB, respecting all the design rules that you have to respect. This should be always the sequence. First simulate, then schematic, and finally the PCB. Once we will have the PCB design, we will have to export the Gerbers in order to send them to a PCB printing company or our CNC mill. Since this is just an example, this won't be a perfect PCB and I'm sure I will make a lot of errors and violate a lot of design rules. But I will show you the main steps in order to make a basic PCB. So let's get started. We first open Design Spark. We can see the menu in the left corner. We first have to create a new project. So we go to File and click New. Here we select a new project. After that we click Browse and we go to the directory where we want to save our project. I've called my folder YouTube. We give a name to our project. I've called it Example. We click Save. We click OK and we should have a new project created. In the project we can see that we have three subfolders: Schematic, PCB and Other. Now we have to create a new schematic. We go again to File, New, but in this case we select Schematic Design. We save it in the same directory as before and give it the same name as the project. We have created the schematic. Now we have to import it into our project. We go to our project and we see that the schematic folder is empty. We click this plus icon and we open the schematic that we just created. You can see now that the schematic is inside our project. We open the schematic. By pressing the A key, we should center the view. On the left side, we can see the Edit menu. We can start adding our components. As I said, you should already have an idea or the schematic prepared. In my case, I will make a simple example of an adapted Arduino Nano. This is my schematic. I will first add the main component, which is the Atmega 328 SMD microcontroller. I suppose that you won't have all the components in the world in this downloaded software. So one option is go to View and click Model Source. And in the search window make a quick search and download the component and use it. You can search for the number of the pins, in this case 32, or maybe for a small part of the chip name. But if you don't find your component and download it here, you can always create it following the manufacturer rules and sizes. So I will show you how to create your own components and add them to your PCB after that. Let's open our component library by clicking the library icon. You can see here that I've got my own library where I already created my Atmega chip component. We click New Library in order to create a new library where we will save all the components that we are going to create. You can use an already created library, but I recommend you to make a new one. We give a name to the new library. In this case I will name it Example and we click Save. We can see the new library is empty. It's time to create our first component. We start a new wizard. We select a normal component and we click Next. In the RS number, just add a random number, such 6 zeros in this case. We give a name to the component. I will name it Example 328P AU for the tutorial. We select an SMD package and a 32-pin component and just one gate. Now we have to select a reference schematic symbol to start with. I recommend you to search a symbol which is almost like the one that you want to create. Let's search for another 32-pin component and use this symbol to create our own. We type 32 and click Find. I think this one will be just fine. Now we have to do the same for our PCB symbol. This is the most important thing because this is the part that will be printed in the PCB. We search for 32 pin pad. In my case this will be just fine because it's almost the same as the one that I want to create. I select the pad and click next. In the pin assignment we just auto-arrange them one to one. We click next, we select the library that we just created and click finish. This is the component editor. We can see our pins, schematic symbol and PCB pad. Now we have to edit all these three parts. Let's start with the schematic. Right click on the schematic and choose Edit Schematic. This is the schematic that we start with. I want to change it in order to have the pins as the real Atmega chip. For that I will choose each 8 pin and I will rotate it 90 degrees. By selecting them, right click on them and rotate by 90 degrees. I do the same for all of them. I put them in the desired position with enough space between each pin and I will scale the component to the desired scale. I do this just by moving the pins and the lines of the component. It's an easy and quick way to do this. You could create your own symbol from zero, add the pin one by one and give it the shape that you want. But this is a quicker way. Once we finish editing, we have to save our symbol. We click save and give a name to our symbol. I will name it example schematic. We select a new library and click OK. We will now give a name to that new schematic symbol library. I will name it example once again and I will click save. Now that we have our schematic, we have to update our component. We go back to the component editor. Right click on the schematic and select properties. Here we select the new library that we just created and inside of that library we choose our symbol and click accept. We can see now that our component was updated. We save the component and overwrite the old one. It's now time to edit the PCB pad. To do that we do the same. Right click on the PCB pad and click edit PCB symbol. Here we are in the PCB symbol editor. First of all we have to download the datasheet of this component. We Google it, download the PDF file and open it up. We scroll down to the packaging information. Here we can see all the sizes and rules that we have to respect when creating our component. Now that we have our datasheet, we go back to Design Spark. First of all, we will move aside the symbol name and the origin. Next, we have to select our scale. For that, click Settings, Units and change the value to millimeters with a precision of 3 decimals. We are ready to edit. First of all, we have to know the width and length of each pin. We can see the pin width in the datasheet labeled with the letter B. We scroll down and we can see that it is 0.45 mm. To obtain the length, we just subtract E1 from E and divide that by 2. In this case, 9 minus 7 divided by 2, we obtain 1 mm. So we select all the pins carefully. Right click and select Properties. Here we give the width and length of the pins. We click accept. Now we need to add the space between each pin. We go to the datasheet and we can see that the distance between the centers of each pin is 0.8 mm. We select the first pin. Right click on it. We select origin and set system origin at the item. In this way we can give coordinates to the other pins respect the center of this one. We select all the parts that are on the right of the origin pin. Right click on the first pin next to the origin and select type coordinate. We type 0.8 in the X direction. We can see that the pins are now separated 0.8 mm between their centers. We do the same for all the pins, always adding 0.8 mm more in the X direction and always giving coordinates to the first pin from the selected ones. Now we do the same in the Y direction, setting the system origin to the first horizontal pin. Now that we have set the space between each pin, we have to add the space between each row of pins. We have to calculate that distance, because the datasheet won't give you that directly. I've already done that here. We can see that the distance between the centers of the opposite pins is E minus 7 times the distance between each pin, and all divided by 2. That gives us 1.85 mm. So we set the origin to the first opposite pin and select all the bottom pins. Right click on the first selected pin and type coordinate 0, 0. We can see now that the pin is centered to the system center, which is the first pin. Right click on the first selected pin again and type coordinate 1.85mm in the X direction and minus 1.85mm in the Y direction. There we go. We do the same for all the other pins, but always changing the system origin to the next opposite pin. We are done. We put in place the name and first pin indicator and we save the symbol. We select a new library and give a name to the PCB symbol. I will name it example PCB and I click OK. I will now give a name to the PCB symbol library and click save. Now we update the PCB symbol in the component editor. Right click on the PCB pad and select properties. We select the library that we just created and select our PCB symbol and click accept. We save and overwrite our component and we are ready to use it. We go to our schematic and click add component. We search for our new created library. Here is our created component. We click add and place it into our schematic. Now we can start our schematic. If you don't have any other component, you can just create it like I did. So, as I said, you need to already have an idea or a simulated schematic to follow. In my case, is this basic Arduino Nano schematic. What I will add first is the ground connection to the pins 8 and 22. To do that, we click add component and search ground or GND. It is just a ground icon. We add that. The good thing about this symbol is that any net that we connect to it, it will be named ground and will correspond to the ground net. As you can see here, the net is named ground as the symbol. We copy and paste the ground symbol. The program will tell us that there is already a ground symbol. Be careful not to change the name of an already named net, because that will mess everything up. We add a new net between ground and pin 22. We can see that the new net is also called ground because we use the same symbol. Next, I will add this crystal oscillator between pin 9 and 10. We can press the R key in order to rotate our symbol. I place it under the microcontroller. I make the connection and next I will add these two coupling capacitors to ground. I will use 0805 size capacitors, so I will search for that number. Any of these capacitors will work because I don't care for their values, just for their PCB pad shapes. Next I will add the VCC 5V connection between pin 7 and 20. Just like the ground symbol, we search for 5V symbol that Design Spark already have. We make the connection and we can see that all the nets connected to this pin symbol are called plus 5V. I next add the coupling capacitors to ground. Next, I will add the reset pin connection. We can see that it has a pull-off of 10k ohms to 5V and a push button to ground. The resistor will be a 0805 as well. In order to program this chip, I will next add this 6 pin of the FTDA programming. Design Spark already has a connectors library. I will use normal PCB pins. We go to connectors library and we select 3 pin connector and we add that twice in our schematic. There we go. Now I will show you a great way to add nets. We add the net to each of these 6 pins. Right click and properties on each of these nets. Here we can add a name to that specific net. We can see here that we named the first one ground. This action will automatically join the ground net to this pin. We do this to all of the 6 nets that we have just created. Now, in order to join the FTDI pins with the chip ones, we add nets to the chip pins as well. If we name these nets the same as the FTDI pins nets, this will automatically join them. In this way we won't fill the schematic with lines. Now we add the 0.1 capacitors to the DTR pin and name this reset pin. We go now to the pin 1 of the Atmega chip and name that net reset as well. Now they are connected. We add the coupling capacitors between a ref pin and ground. Now I want to have some outputs and inputs. I will use digital pin 2, 3 and 4 and analog input A0 and 1. Just as before, we add the 5-pin connector. Name the connector nets as we can see here and the Atmega pins the same, and the connection is done. We type the A key to center and we save our project. It's time to pass our schematic to a PCB. To do that, we go to Tools, Translate to PCB. This will start a new wizard. We specify our units, in my case millimeters, and a precision of 3 decimals. I want to make a double layer board. I will make my board 5 by 3 centimeters. We can choose to auto position all the components or to arrange them outside the board. We click Next and give a name to our PCB, just as the schematic. We click Finish. This is our PCB. Now we start adding the components. We will first center the most important component. Where you will put the components it's up to you, but I can give you some tips. Put the microcontrollers as center as you can. The coupling capacitors as near as the needed area. Connectors as near to the board outline. Try not to make the tracks too long and always make a 40-degree angle. To flip the sides of the component, just select it and press F. To rotate it, press R. Now, a very important step is to set our design rules. We click on the settings icon. First we go to track styles. We can see that we have 2 styles. We can create as many as we want, but in this case power and signal it's okay. We give a bigger width to the power line. The maximum width of the signal track will be 0.45 mm because this is the width of the smallest pin that we have. Another important step are spacings. You have to know the rules that your manufacturer gives you. In my case, I know the settings of my CNC milling machine. I know the maximum width that it supports and I know the spacing that I want to give to my PCB. Now in the path styles, I have to set each hole to 1 maximum decimal because I don't have drills with the 0.01 sizes. So I have to use just 0.6, 0.8, 0.9 or 1 mm drills because of my CNC milling machine. Once we set up all the rules, we are ready to trace all the tracks. Try always to make 45 angles of your tracks. Press double V key to change the type of your angle. If you want to change the side of the board where you want to add your track, just press L to change the layer. If you are routing on the top layer and press L, it will automatically create a via for you and you will be able to keep routing on the bottom layer. If you want to change between types of your tracks, just press S and select between the types of the track. We have to constant check for good connection, and for that once in a while we go to Tools and choose Forward Design Changes, and this will give us a report of the connections. When all the tracks are traced, we have to check for design errors. We click on the design check and run it. We can see that I have a total of 5 errors. I can see those errors with the pink color on my PCB. If we zoom in on the error and keep our cursor above it, it will show us the error. Of course, it's a spacing error. We've told to the program that we want a maximum of 0.25 mm between each track. We have to correct this. Finally, when we have no more errors, we have to pour copper on our PCB. In this way, the CNC machine won't work an entire day to mill all the copper of our PCB. We select the Pour Copper Outline tool and we create a rectangle around our PCB. One for the top layer and one for the bottom one. Just press L to change of layers. We select each rectangle and click the Pull Copper tool. I recommend you to fill the PCB with gram track. Our PCB is done. In order to mill it or send it to a PCB printing company, we have to create the Gerbers. For that, we go to Output and select Manufacturing Plots. We select the layers that we want to print. In my case, it's just the bottom, top and drill layers. We select our settings and click Run. Now I will use FlatCam software to create my G-code file because my CNC machine works with G-code. I open FlatCam. I open one of the Gerbers that I have just created. Let's make first the top copper one. We select the Gerber file. We add our machine settings and create a geometry. Now we select that geometry and give the values of the feed rate and Z-cut of the PCB copper and generate a G-code file. We now select that file and export our G-code. I use Universal G-code Sender and a Gerber firmware to print my PCB, but you can use any CNC mill program that you have. We are done with this tutorial. I've shown you the basic steps to create a component, the schematic and the PCB design, and how to mill it after that using the Gerbers. With a little bit of practice, you should be able to make a little bit more complicated design like this one that I've designed right here in Design Spark. I hope you like this tutorial and that it will help you. Check the description and my webpage for more information and for all the main hotkeys in Design Spark. The links of the software are in the description as well. Thanks again and see you later, guys.